Hi, we're back. New chapter, new chapter. Um, this chapter is about probabilities, and when we calculate probabilities, we have to do some counting. And so counting can be pretty confusing because we have to count all the number of different ways things can happen. So in order to help ourselves count, we have some kind of tools or different, I guess you could call them rules or, I don't know, strategies to count up all these different possibilities. So this first page that we have here is just to kind of get you thinking in the right way about reducing certain expressions we might be dealing with. Okay. So I know these seem a little bit odd, these expressions, but let's just get started with how could we possibly simplify some of these. So if you have 4 times 3 times 2 times 1 over 3 times 2, would that reduce at all? You could reduce, right? And you could take this 3 times 2 part, because you're multiplying all of them together, and you could reduce it with the other 3 times 2 part, and this would end up being just 4. Agree? Okay. Same thing with this number 2. We have this whole 7 times 6 times 5 times 4. It seems kind of weird. Over 4 times 3 times 2 times 1. Take that 4 times 3 times 2 times 1 stuff and cancel it out with that 4 times 3 times 2 times 1 stuff, because that would be the same as, that would be the same as 1. Like 4 times 3 times 2 times 1 over itself is the same as 1, so you can just get rid of it. So this ends up being just 210, which is the product of 7 times 6 times 5. I'm going to jump to number 4 and then I'll go to number 3. Have you ever seen the exclamation point in math as a symbol? It means, well, it's factorial is how you say it. So you would say this as, you'd say this as 5 factorial. And the factorial part means that you multiply by that number times the next number smaller, the whole number smaller, times the next whole number smaller, all the way down until you get to 1. Okay, that's what the factorial is. It's just it's like a shortcut, because oftentimes when we're calculating how many number of ways like you're counting up the number of possibilities or ways for something, you end up doing like 7 times 6 times 5 times 4 times 3 times 2, and you end up doing that over and over again. So they made a shortcut for it, and that's what this exclamation point is. It's a button on your calculator, or it's a way to represent writing 5 times 4 times 3 times 2 times 1 without actually writing it all down. So it's just a shortcut way. So this would end up being, what, 20 times 6 is 120. Okay, so that's factorial. So that's why you're seeing all these weird expressions like 8 times 7 times 6 times 5. This is like from 8 factorial, right? This is like 4 factorial. Yuck. 4 factorial, and this is like 3 factorial. Anyway, so part of 8 factorial would cancel out with 4 factorial, right? And then the 3 times 2 times 1 part, 3 times 2 is 6. That would cancel out one of those 6's. So really, this expression would be just 8 times 7 times 5, which is 280. So that's just a little bit of, hey, what's factorial, and how can you manipulate these expressions and simplify them? Yeah.
Would you ever write 2 factorial?
I mean, you might write it, but, 2 factorial is just, yeah. A little bit more about factorial, just jumping ahead here. 0 factorial is defined as 1. Okay, so you might see 0 factorial. And I guess this is clipped from the book, so we have this little bit down here about factorial as well. So if you want to pause that and read through the technical way they explain it, there you go. But we'll just jump into, all right, we have some factorials in our expressions. How do we simplify these? So 7 factorial over 4 factorial can be rewritten as 7 times 6 times 5 times 4 factorial over 4 factorial. So instead of writing the whole like 7 factorial out, I can chop off part of it. And then guess what happens to those 4 factorials? They will reduce, yep, cancel out. Okay. So cancel those puppies out. And this would just be 210. All right, same thing over here. We have 11 times 10 times 9 times 8 times 7 times 6 factorial over 6 factorial, because you do the 8 minus 2 first. And so then you can cancel off these, and we are left with just the product of 11 times whatever all that stuff is. I think it was like, I'll do it again here, 11 times 10. What was it? Yeah, 55440. Okay. So the numbers get pretty big pretty fast when we're talking about working with factorials and counting all the number of ways things can happen. Number 7, same type of thing, right? So this is going to be 8 times 7 times 6 times 5 factorial. So the 5 factorials will cancel out. So cancel, cancel. And then 3 factorial, that's the same as, this is where you can just start to figure out, okay, 3 times 2 times 1 is 6. So that 6 cancels out with that 3 factorial, leaving 8 times 7, which is 56. Okay. So what we're going to do now is we're going to start counting things, counting up the different ways things can be. And when we are counting up the number of ways we can arrange things or have things, sometimes order matters and sometimes order doesn't matter. So when we're talking about permutations here, this is going to be a big thing to recognize that order matters. Okay, I'll give you an example of when order matters. A couple examples. Let's say there's how many people in this room right now? 8. So there's 8 people in this class right now. What if I said, all right, I'm going to take 3 of you, okay? And I am going to, let me think. All right, let's say we have this row of desks right here, okay? And so let's get rid of this one desk. Sorry, that was loud. So we have 3 desks in this row, right? So how many ways can I arrange the 3 students that are sitting in that row? So let's say we have, here's my row of desks, first, front, middle, and then the back, right? So if I have 3 students in that row, how many different ways can I organize those 3 students? Because here's kind of what we're going to be doing. Most people said 9, right? That's what they said last hour too, and then that's not correct. What's that? 12. Nope, not correct. See, it gets tricky. So let's draw a picture. Let's have a strategy here. So let's say we have student A, B, and C. Basically, how many different ways can I arrange those letters to make different arrangements? Right? Well, I can have A in front, so that'd be A, B, C, or A, C, B, right? Now what if I had B in the front? Yeah, and so you can see now someone yelled out 6. And so they realize, oh, I see the pattern now. B's in front, so I can have B in front and then switch those 2. And then I can have C in front and I can switch these 2. So it's CAB or it's CBA. And so now that's covered all of my possibilities or possible arrangements. So there's 6 ways you can fill that desk, those 3 desks, right, with 3 people. So if I pick 3 people, there's 3 ways I can fill those desks. What did I essentially do there? I essentially took how many people were possible for the first desk? 3, right? Okay. How many choices did I have to put in the front? 3. And then after I made that decision, how many choices did I have for the second one? 2. And then for the third one, 1. So really, you kind of maybe can see where the factorial part comes in, is when you're calculating these, I guess, permutations, the number of ways you can make that arrangement, you end up doing a factorial. That's why we have that whole button anyways. So this ends up being 3 times 2 times 1, or 6 ways, which wasn't too bad because it was just 3 people, right? Okay. But now what if I say, instead of doing that, what if I say like, okay, what about Kate's row over here? How many desks are in this row? 5. Okay, so now how many ways can I arrange that? And now let's take, like, if this classroom was full, let's say I had 30 students in this classroom. How many different possible ways could I arrange that row of 5 desks with all 30 of the students in here? Okay, well that's going to look like this then. That's going to look like, no, there's 30. So it's going to look like 30 times, whoops, there's 5 desks now. 30 times 29 times 28 times 27 times 26, right? And so, what's up? Because there was only 5 desks in the row. That's why I stopped at 26. So this is part of a factorial, isn't it? It's like part of 30 factorial. Okay? And so what we have is a rule or a button, a little algorithm that's built in our calculators to do this little calculation for us, and that is called permutation. It's this button right here in your calculator, 7 permutate 3 at a time. Okay, it's this rule right here. So the rule is that we take, in this case, if I relate it to what we just did, we would take 30, permutate 5 at a time. So basically, how many ways can I select 5 from 30 and arrange them if the order matters? So what happens now when you follow that rule is, and the 30 is the n, right? And the 5 is the r. So you end up with 30 factorial divided by 30 minus 5 factorial, which is kind of what we were just doing on the previous page. 30 factorial over 25 factorial, which ends up being 30 times 29 times 28 times 27 times 26 times 25 factorial, I'm running out of room there, over 25 factorial. And then what happens to the factorials is they cancel out, and you're left with 30 times 29 times 28 times 27 times 26, which is what we just talked about as being the number of ways you could fill those 5 desks. So we have these rules, these little algorithms, these buttons on our calculator that save us time, just like factorial buttons saves us time from having to write out all of that stuff or to push all those buttons on the calculator. Like, can you imagine like having to do like 30 factorial and push all the buttons on there? Yeah, you'd probably push one wrong button and everything would be wrong. If your life depended on that answer being right, you'd probably triple or quadruple check it to see that you didn't push a wrong button, right? So that's what these permutation buttons are for, and that's what this little rule is for, is basically like a shortcut, okay? And so when you are using permutations, the order in which you are counting up your different ways or things matters. All right, let's jump to the next page. This is just finding the button on your calculator. All right, so I'll show you where the button is on the Inspires. So on the TI Inspire, if you go to the home screen and you go to this calculator, And from the calculator, you go to Menu, Probability, and then it's right here. You got factorial, permutation, combination. So if I go to permutation, it'll say NPR like that. And I think the problem was 9 and 3, so I go 9, and then I hit the comma button, and then 3, and hit enter. Okay, so each calculator, unless it's a very, very basic like mini calc, will have these buttons built in. All right, well, I'll show you this. Actually, this is a good clip I'll show right now. Here's an example of where order would matter, okay? I don't know if the audio will come out, so I'll have to hold it close.
They're picking the lottery balls. Here's today's mega lottery picks worth $34 million. The first number is 44. The next is 2, 38, 24, 21, and 54. Cripes! I was so close. They had all the right numbers, but in the wrong order.
So, does order matter or not? Not for the lottery. So, in the lottery case, we would not be needing to use a permutation. We would need to use what's called a combination, okay? And so, I guess since I just saw that, I'll just jump to the next page. But all these on this page, you want to be able to find that button on your calculator and just know how to use it so that you don't have to do all that calculating and stuff longhand. The whole point is for you to be able to use the button, understand how it works, and then boom, you got your calculation. All right, so we'll move on from there. I guess I have a couple permutation examples. We'll just do these and then we'll go to combinations. But like I said, permutations are when order matters. So if you know anything about baseball, you have to have a batting lineup. And in the batting lineup, you have to have the right order every time. If you bat out of order, then I think it's like an automatic out or something like that. So you can't bat out of order. So if we have a team of 12 players, right? How many ways can you set the batting order if all 12 players bat? Well, technically you don't really need a permutation for this, but I think it just makes the calculation cleaner. I'll show you what it looks like longhand. Was how many choices do you have for players to lead off? 12 times 11 times 10 times 9 times, and then you can kind of see how this ends up just becoming 12 factorial, don't you? Okay. And so 12 factorial, if we did a permutation, because for this, definitely on this situation, order matters. Okay. So if order matters, that's where we have to use permutation, which is the only one we've talked about so far, but this would be then a permutation of 12, and we would permutate all 12. So when you do the rule for that, the permutation rule, that would be 12 factorial divided by 12 minus 12 factorial. But 12 minus 12 is 0, and 0 factorial is 1. So this ends up just being 12 factorial. So you'll see if you permutate all of your choices, like 12 permutation 12, it ends up just being 12 factorial, which is a pretty big number, isn't it? What is 12 factorial? 12 factorial, that is 47,001,600, or 479,001,600. Cripes, that's a lot of different possible batting lineups.
So if you, would you have to write that whole number out on a test, or could you just leave it as 12 factorial?
I would want you to write the whole number out, yeah. Unless it just said leave it. Because I want you to know where these buttons are on the calculator, right? If you're only batting 9 players, then it would be order matters, so it'd be 12 permutation, 9 of them at a time. So it's a little less now. Now we have 12 factorial over 12 minus 9 factorial. So really this is, you're dividing by, what, a 3 factorial or something. So find that button on your calculator, and 12 PRB. If I'm doing it on the TI-30, there's a PRB button. So if you're wondering on that, I typed in 12 on my calculator, and then I hit the PRB button. And then from the PRB button, I chose NPR button. And then after that, I pushed enter. And then after enter, I had to type in 9. And then I hit enter again. And then I end up with an answer of 79,833,600. So still quite a bit. 79,833 something thousand 600. So a lot of choices. You see how hard it is to be a baseball coach. Imagine that. You're sitting there pondering 79 million different lineups. It's outrageous. Okay. This is the old secretary, president, vice president. All right. So does order matter? Yes or no? If you are going to pick 3 people out of 5 and say, you're going to be the president, you're going to be the vice president, you're going to be the secretary, does the order matter? It does, because we're giving them roles, right? It's not like we're just saying, hey, I'm going to pick 3 out of you 5 and you guys are all going to go sweep the hallway. Okay, all of you are equals. Get a broom. It's not. We're not doing that. We're saying, hey, you're the leader, you're the vice leader, and you're the secretary. So order matters. So this is going to be a permutation of 5 people taken 3 at a time. Put that in your calculator just like that. Hit enter, and you end up with what? 5 times 4, is it? Times 3. So 60? Do you know where the button is in your calculator? Did you get 60? Again, this is a smaller problem. So if it's like, how many ways can I pick 3 people? You could just write out like, oh, okay, I got 3 different possibilities like that. That's 5 for the first one, 4 for the second, and 3 for the third. Okay, it's really not that much of a shortcut to push the permutation button, actually. But it might be a good habit to just get into.
So you don't care if, like, on homework we just type it in?
No, I need you to know what the permutation is. But, sometimes you might not use it because it's not as big of a problem. Last thing to talk about is combinations. So like sometimes the order doesn't matter. Like I was just talking about, like, hey, you 3 get in the hallway, sweep up. I pick 3 of you 5, you're all equal. It doesn't matter which one of you I picked first. If I pick like you 3 and I go, hey, Aaron, Carissa, and Jada, get in the hallway. I picked you 3 to go clean up, pick up scraps. It doesn't matter if I picked Aaron first, Carissa second, Jada third, then I picked Carissa first, Jada second, Aaron third. You're all the same. Just go sweep up. But if I say, hey, I'm going to pick 3 of you guys and I'm going to make you guys like a little bit of a cabinet here. One of you is going to be the president and then the vice president and the secretary. Well, then it matters who I pick for what role. So order matters there. So sometimes order matters, sometimes it doesn't. If it doesn't matter, then we don't have as many different combinations of things. So that's from the last hour. The difference in the formula from a permutation to a combination is there's one thing. I'm going to enlarge this. Whoa! Whoa! Even bigger yet. Whoa! All right, the one thing that is different is this part right here, the r factorial. Otherwise, it's the same exact formula. Okay, so what that extra dividing by r factorial, and remember r is the number of things you're selecting, is that undoes all of the ways you can arrange those r things. So like if I say, hey, let's pick 3 of you people and make a cabinet, vice president, blah, 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 Well, then there's 8 of you in here right now, right? So that would be 8 times 7 times 6. That would be the number of ways if order mattered. And so that is what? Gosh, 56 times 6, that's going to be 336. Okay, so 336 is when order matters, right? But if order doesn't matter, then I don't really care about, and remember before, how many different ways can I arrange 3 things? I could have ABC, I could have ACB, I could have BAC, I could have BCA, I could have CAB, or I could have CBA. There's 6 ways to organize that, right? So if I want to undo those 6 ways, I would have to divide 336 by 6 because I have 6 times too many different combinations. Because I don't care if I pick the group ABC. ABC to me is the same as BAC. It's the same 3 people if order doesn't matter. Get out of here. Go sweep up. So if you don't account for order not mattering, you're going to have 6 times too many or R factorial times too many. Because this was 3, so we had 3 factorial, which is 6 times too many combinations. So that's why in the combination where order doesn't matter, we're doing this divide by R factorial because we're kind of undoing the fact that order matters, so we're dividing that out so order doesn't matter. Okay? Hopefully you followed that. All right, so here's the combination rule, and that's another button on your calculator. So find that button on your calculator. It's in the PRB if you have a small one. If you have like a graphing calculator, it's probably in a menu somewhere. Can't find it, let me know. And so this ends up being 9 factorial divided by 9 minus 4 factorial, and then you got to divide by another 4 factorial. And this is the new part that says, hey, I'm dividing by that because order doesn't matter, so I'm going to undo all the different ways you can arrange those 4 items. It doesn't matter which order they end up being in. Okay, so you click the button on there, and that ends up being whatever it is. I don't know. 9 times 8 times 7 times 6, that's 5 factorial, so that cancels out. And that's over 4 factorial. 4 factorial is going to be 12, so I can take one out of there, and I can take one out of there and make that a 2. And so it ends up being 14 times 9, which is what? 126, yep, that's right. So you could just hit the darn button, and then you'd get 126, and you wouldn't have to do all that stuff I just did. But why did I cross out to you? Yeah, I was kind of cruising there. So this is, actually I messed up a little bit here. I got to do times 5 and then times 4 factorial. No, I didn't. I didn't mess up. I just didn't write it all out. So 9 times 7 times 6 times 5 factorial, right? And then this right here was 5 factorial. So that canceled out with that. And then 4 factorial is 4 times 3 times 2 times 1. So what I did here was I took the 3 times 2 and I crossed that off with the 6 there, and then I took the 4 and I divided 4 out of there and I left it 2. So I have a 2, a 9, and a 7. I just did it the long way, in a fast way. And so this is why we just have the button. Just push the button. Just take the calculator, use the button. Use the button on the calculator. That's why we have it. All right, so find your button and be able to use it. Oh, mamma mia, let's talk about a pizza. All right. This is my good favorite one about combinations and order not mattering, okay? So let's say you call up Guido at the pizza shop. That was stereotyping. I shouldn't stereotype. Let's say you call up Rick at the pizza shop. Yep, this is Rick's Pizza. It's Rick speaking. Hey, Rick, I'd like to order a 3-topping pizza. None of the toppings should be repeated. Can you tell me how many different possible pizzas that is, please? Rick's like, well, yeah, I can do that. I remember this from Algebra 2. All right, so we have 15 different toppings, and order doesn't matter for pizza because if I put on the pepperoni, sausage, mushroom, and I pick those 3 toppings, it doesn't matter what order I put them on. It's the same pizza. If I put the pepperoni on first and the sausage on second and the mushroom on third, or if I put the sausage on first and the mushroom on third, it's the same pizza, right? Okay, so order doesn't matter. Some of you might be like, oh my God, yes, it matters. If you put the pepperonis on first, then the other toppings are going to cover them and they aren't going to get crispy, and technically it's not the same pizza. Yeah? Good, 2 minutes. So the order doesn't matter. So if the order doesn't matter, then I'm going to use a combination. There's 15 toppings. I'm going to take 3 at a time. Okay? You push the button on your calculator and you end up with, I think it's like 455. Is it right? So you end up with 455 different pizzas. Bada bing. Same thing with the last problem on here is this is a silly math book problem. Katie, this isn't you, Kate. It's Katie adopting kittens. There's 11 kittens. She wants to take 3 at a time. So there you go. So anyway, that was a long lesson, and I had a nice nap in 6th hour. So hopefully you're well rested. Homework is a worksheet. All right, ciao.